So chapter number 4, of course, this is the overview of assembly language. So in this chapter, we are going to discuss about the structural view and step-by-step procedure, how we are going to discuss or how we are going to write the assembly language properly and in a structured way. So first thing is we need to know that in assembly language, we actually write the code line by line. That means they're called statement. So in this assembly language, we have three different types of statement. They say different class or different type, same thing. So there are three types of statement in assembly language. First type, they call it executable instruction, or in short, just the instruction. Okay, so this type of instruction is, of course, first of all, this is executable. That means the processor actually directly have an instruction what to do, and then according to that instruction, the processor do the task. All right. So this is called executable instruction. So in this executable instruction, we have one important part, which is called operation code. As you can see, operation code, in short, opcode. Okay, so we have opcode or operation code in this executable instruction. And then another important thing is this type of instruction or this type of executable instruction is actually converted from assembly language into the machine language directly by the assembler. That means there is no in between interpreter or compiler between the code and the machine language. That means the assembler directly convert the assembly language executable instruction into the machine instruction or machine code or machine language, so that our processor can understand and then can do or can act accordingly. Okay, that's why they call it executable instruction, or in short, instruction. Okay, second type of instruction or second class is, we call it assembler directives. Okay, assembler directives. So in assembler directive, first important thing is actually non-executable. Previous one is, we call it executable, but this one, assembler directives, these are non-executable code. That means it is not given instruction to direct instruction to the processor that what to do. It is actually given the instruction to the assembler that what that assembler needs to do it. That means it is not a direct code. It's actually kind of indirect code. Okay, because these types of code give instruction to the assembler, all right, to do something. Okay, and then assembler do the rest, not the processor. Okay, that's why these are called non-executable. Fine. For example, the data allocation. Data allocation is assembler directive. Data allocation is not directly done by the processor. The data allocation is actually done by, or the processed by, the assembler. All right. So the data allocation is one kind of assembler directive statement. Okay. So that is the second type. Third type is called macros. Macros. What is a macro? Is actually a short form of a group of statement, a group of code. Very similar, very similar to our function. In our high-level language. In our high-level language, you have a function, right? Or where we name the function, call the function, and then each of the function is actually a combination of several code in a high-level language. So whenever you call the function, the full code is actually run and give you the result or output. Here, exactly same. If you want to run that group of code, you actually just need to call the macros. Okay, because the macros is actually related to a group of statement. That means that macro will, whenever you call the macro for the running, for running or for added into the assembly language, actually execute those group of statements. So that is called macros. As I said, very similar to the our function in high level language. Okay, let's see how the format. So this is actually the format, general format of how we are going to write the assembly language code. Okay, and if you see any kind of level like this, I mean not level, like third bracket in any format. By the way, this is not the code, remember, this is the format of writing the code. So if you see in any kind of third bracket in any kind of format of assembly language code, that means those are optional. That means those are not mandatory to write. That means if you don't write that part of the code, it will not give you any error. Okay, but it depends on your program. That means doesn't some of the program use it, doesn't the program doesn't use it. Okay, but technically all of them are right. So as you can see that in this format we have three optional things. One is the level, another one is the operands, that means the variable name, another one is the comment. That means these three things is actually the option. So it depends on your program, you can write all of them or either one of them. Okay, so that is the code. We have level, mnemonic. By the way, mnemonic is actually the what is the operation we are going to do. Okay, so that is our format of the code. One more thing is the level in the execution instruction is followed by a colon, but not in the directive statement. That means whenever you have an executive instruction, I mean not executable instruction or just the instruction, this one executable instruction, in that instruction we actually have a colon after the level. If you have a level, there will be a colon if it is executable instruction. If it is not executable instruction, then there will be no colon. Okay, I hope you can see in the book there sometimes is writing data and then colon. Sometimes it's writing the iteration and then the colon. So this is actually show that these are executable instruction. Okay, not the directive statement. So that is another important part. So the next part is actually the data allocation. I hope you know that every language, the basic or the most important part of any language is actually the data allocation, because we need to know our types of the data. We need to know variable type. We need to know how we are going to define the variable, and of course how we are going to define or allocate the memory for running our code. So that is actually data allocation, and as I told you before, data allocation is actually done by the define directive, the define assembler directive. Okay, that means this is an assembler directive. That means this is a second type of code, not executable. Data allocation coding are not directly executable. All right, these are assembler directive. Okay, so look at the format again. So this is the format of the defining the assembly language um, uh, variable name. Then we have define directive. We have initial value, and we have other initial value. And as we know that in the format, if there is a third bracket, that means these are optional. So we can easily guess that variable name is optional, and several initial value, that means one initial value is must, but if you have several, that is also optional. By the way, this is entirely depends on your program, that what you're actually going to write. Most of the time we actually using the variable name, but according to the technical rule, that if you don't write the variable name, still technically that is correct. Okay, so that is our code. Let me show you an example, and then let me explain this one. In the book, if you look at the book, that okay, let me give you this example. Look at this example. Sorted db 79h. If you compare this line with that line, what we can understand is, let's match. First one is actually our variable name. Although they said this is optional, but in this case we need this variable. That's why we write it. Okay, don't think that we don't need to write this in this case, but we need to write in this case. Okay, okay, so this is the variable name. After that, we have defined directives. By the way, we know that already there are 5 types of defined directives: db, dw, dd, dq, and dt. And we know that d means defined, and the other words means byte, word, double word, quad word, and 10 bytes. So that is our 5 different types of defined directives. Make sure you remember this one. So we have, so as we are comparing, so first one is the variable name. This is the variable name. After that, we write defined directives. That is a must thing. We have to write it because it is a must. After that, we have initial value. That means it is also a must that you have to have an initial value. Okay, initial value of this variable. So this is the 79h. By the way, why you write h? Because this is an hexadecimal number. This is an hexadecimal number. That's why we write 79h. Original value is actually 79. Okay, so that's how we can define our data. All right, so that's how we can define our data. And we know that we have actually the same line of code. The same line of code we actually can write several ways. We can write it in this way. It's the same code because 779 hexadecimal number is actually equivalent to y. So if you write y or 79 hexadecimal number is the same thing. If you write the binary number, that's why they write b, it's also the same thing. So we can write the code, assembly language statement code or statement, in several ways. Okay, that is the 3 example actually how we can write it. Okay, another example, this is very important one. Look at this example. This example is actually shows that I am presenting. So this example is actually shows that this is our variable value. This is the defined word. That means we are going to allocate the word. That means word means 2 byte. We are allocating 2 byte into the memory, and this is the number, initial value. This one, initial value of that variable. Okay, so that means the value of this is actually this number, integer number. But we know that we need to store the value or any data is actually by hexadecimal or binary number, because the machine language can only understand binary or hexadecimal number, right? So we need to convert this into the hexadecimal number. So the equivalent of this 25159, by the way, is just an example of a value, decimal value. Equivalent of this integer value is this hexadecimal number 6247. Okay, 6247. So whenever the assembler try to save this value into the memory location, according to the Pentium processor, they actually use little ending byte ordering. So what is it, little ending byte ordering? Little ending byte ordering means whenever you have a value, let's say we have a value of 6247, and we know that for hexadecimal number, one value or one number is representing 4 bits of binary number. That means 47 is 1 byte, 4 and 4. 62 is another byte, 4 bit plus 4 bit. So according to the Pentium processor, they actually store the least significant bit first and then the most significant bit. Here the least significant bit is 47 and the most significant bit is 62. So according to the Pentium processor, let's say we actually have 2 bytes, right? We are defining DW, that means we have 2 bytes. And we also know that in assembly language, whenever you allocate the memory, they actually allocate the memory in serially. Not like that, one byte is here, another byte is far away. Not like that. The assembler define or allocate the memory location serially. So in this case, we actually have 2 bytes. Okay, 2 bytes. So this is the first byte location, that is the second byte location. So according to the Pentium processor, we are going to save the least significant bit first. That means we are going to save the 47 first into the first byte, and then the 62 into the next byte. We are not going to have the other way, 62 first and 47 next. It is not possible. According to the Pentium processor, it is not possible. Okay, I hope you understand that we define two byte number 1, byte number 2, and according to the Pentium processor, we store the least significant bit first, and then we store the least significant, most significant bit. That's why 47 first and 67 at the end. Let us see another example. I hope you will understand. This is a similar type of thing where we have variable called total, and we have defined dd. I hope you remember that dd means define double word. Double word means two word. If one word has 2 byte, double word means 4 byte, right? So we have 4 byte, and this is a very large integer number. Okay, so if you convert this large integer number into the hexadecimal number, so this is actually the hexadecimal number. Look, very large hexadecimal number, right? So we need to store this large hexadecimal number into dd, that means 4 bytes location. So these are the 4 bytes. Byte number 1, 2, 3, 4. By the way, it's actually starting from 0. That's why they have written 1, 2, 3, 4. So if the value of x is 1, that means first, second, third, and fourth byte. Okay, so let's see. In the first byte, we know that Pentium processor is actually using little ending. That means least significant bit first. We have to store it and then go for the other one. So what is the least significant bit here? 4h, right? That's why we store into the first byte, we store 4f. After that, 86. After that, 5a. So third byte we store 5a, and at the end, the last byte will actually be in store the most significant bit, which is 20. Okay, so that is actually the explanation. Okay, I hope you remember. I mean you understand. So next thing we have discussed that there is a range of these 5 different types. Make sure also we can understand this one. It's very simple. This is dB means 1 byte. 1 byte means 8 bit, right? So that's why it's maximum 2 to the power 8. DW means 1 word. Word means 2 byte. 2 byte means 16 bit. That's why maximum is 2 to the power 16. DD, that means 4 byte. 4 bytes means 32 bit. That's why maximum is 2 to the power 32. And this is DQ, quad word. Quad word means 4 bytes. No, I mean 4 word. 4 word means 64 bits. That's why maximum is 64. That's how we can remember. Okay, so that is also the range. And then we know that by the way, this is another example. This is another example that how we can by the way, let me just pause. So now we are going to discuss about the multiple definition. So what is multiple definition is, that means instead of writing several times, we actually can write in one time if you have several data like as array. But before that, let me show you one thing that previously I told you that whenever you define any data, the assembler is actually allocate the memory location serially. Okay, so look at this example. We have 3 variables: sort, value, and total. Okay, first one is byte type, second one is word type, and third one is double word type. So look how actually the value is actually stored into the memory. So db means 1 byte, that means first byte. So first byte is the variable sort. Okay, so in first byte we store sort. In the second one, the value, we have word. Word means 2 byte. That means second and third byte will be the variable of value. So second and third one. as this is the value, initial value. So if you convert into the hexadecimal number, it will be 47 and 62. And we know that according to the rule, 47 will store first and then 62. That means in the third byte it will be 47 and second byte 47 and third byte is 62. Fine. So that is our variable called value. Next we have total variable, and total variable is DD type. That means double word. Double word means 4 byte. That means 1, 2, 3, 4. Next 4 bytes serially will be the variable called total. Okay, total variable. So the value is here, this one, and this is the hexadecimal number. So according to the rule, we know that it will be, this one should be the least significant bit, 4H first, 4H here, then H6, then 5A, and then 80. So that is a proof or an example that whenever you write in this type of code, the assembler is actually allocate the memory location serially. Okay, serially. That's all. So let's see the example of multiple definition. This is the way we actually can do the multiple definition. That means the message is a variable where db store w, another db store w, because one character can be stored into 1 byte. You cannot store many character into the 1 byte, because one character required 1 byte of space into the memory. Okay, so that's why we need to write several times. That we can write it in this way, we can write it in that way, we also can write it in that way also. So message is the variable, db welcome and exclamatory sign. That means how many we have? I think it's 7 or 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 byte, because each of these is 1 byte, so there are 8 byte for message. Okay, so that is called multiple definition. We can do this way. We can define our multiple definition. We can also write in this way, or we also can write in that way. By the way, we also can write in that way also. That means exclamatory sign, not exclamatory, sorry, quotation sign in between this is the value. If you write comma, that means 0D is another value and 0A is another value of message. Okay, that means now the value of message is BYE, then 0D and 0A. So that is the value of message. Okay, so that is called the multiple definition. We also have another thing, multiple definition, which is called the array. How we are going to define an array into the assembly language. So this is the way we can define the array into the assembly language. How? We need to write times. This is the keyword, TIMES, times. By using these times, we can define the array or table into the assembly language. So how we write it? Name of the array. We have to write the times. How many elements in that array? Which type of data of each array? And the initialization of the first element. Initialization of the first element. That's what it means. Let me tell you again how you are going to define an array in assembly language. First of all, variable name. Secondly, you have to write the times in capital letter, TIMES, times, the capital letter, the keyword, and then how many elements in that array. If you have 10 elements in that array, you write 10. If you have 1000, you write 1000. Okay, so how many elements, and then each element is which type. Either is a byte, word, double word, or 10 words or quad word. So this is the type and the initial value of the first one. So that's how we can define an array in assembly language. Fine. Okay. I think let's tell you the last topic of today. I mean revision, which is the symbol table. Okay. So what is a symbol table? Is in symbol table, as I told you that we have in assembly language, whenever you write this way, this line by line, the assembler is actually defining or allocating the memory location into the memory serially. right? So if you know the first starting address, you actually can easily find the next address. For example, look at here. Look at here. It's actually whenever you write this code, in the memory, all of them are in serially, right? So if you know the first address, it is very easy to find out what is the address of this variable. Very easy, right? Because first byte, because it's the db means 1 byte. Fine, no problem. That means the next value, the next variable will start from second place because it's just 1 byte. Because it's just 1 byte, so value variable will start in the second place. Very simple, right? So and when the total variable will start in which position, because this one is 1 byte, that one is 2 bytes, so we actually have 2 plus 1, 3 byte. So 3 byte is occupied, so the total variable will start from fourth byte, right? Fourth byte. So this is how we actually can make a table, that how we can find those variable into the memory location. Those information is called a symbol table. So assembler make a table where we have a name of the variable and the offset value. Offset value is where actually your variable started. Okay, so combining these two information, we can have a table which is called symbol table. Okay, symbol table is very important, where the assembler can find the data or find the information into the memory very easily. Okay, fine. So that is called symbol table. So I think that is all for today.